In this video, I will calculate the factorial of negative 0.5. The result is the square root of pi. So first, let's look at the factorial of an integer. When n is an integer, n factorial equals n times the factorial of n minus 1. Therefore, 5 factorial is equal to 5 times 4 factorial and equals 5 times 4 times 3 times 2 times 1 factorial. And we define 1 factorial to be 1, and therefore 5 factorial is 120. What about 0 factorial? Because of this equation, we have 1 factorial equals 1 times 0 factorial. Therefore, 0 factorial is 1. What about 0.5 factorial? To deal with the factorial of a fractional number, we have to define this gamma function here. The integral of x to the power of z minus 1 times e to the power of negative x dx. X is from 0 to infinity. So over here. And therefore, we will be able to prove this gamma of z is equal to z minus 1 factorial, or the gamma function of z plus 1 is equal to z factorial for all integers. And make sure that you understand this is a smooth function. It's not continuous at several negative numbers, but it's a smooth function. First, let's prove this gamma function of z is equal to z minus 1 times gamma of z minus 1 for all positive integers. Alright, so first, this is how gamma is defined. And then we know the first derivative of e to the power of negative x is negative e to the power of negative x times dx. Therefore, e to the power of negative x dx is negative d, the differential, exact differential of e to the power of negative x. So this is a mathematical transformation here from here to here. We just need a negative sign here. And then I'm going to say x to the power of z minus 1 is my function f. E to the power of negative x is my function g. So f dg equals d fg minus g df. And then there's a negative sign here. So negative f dg is g df minus d fg. So this is g, this is f, this is d fg. And fortunately, this one is just 0. This is very easy to integrate. The integral of the exact differential of a function is itself, the function itself. So we copy this function here. We integrate this function from 0 to infinity. And when x is 0, this part is 0. When x is infinity, e to the power of negative x is 0. Therefore, this part is simply 0. We have only one integral left, this one. And then we can take the first derivative of x to the power of z minus 1. It's z minus 1 times x to the power of z minus 2. So it's here. And then don't forget about dx. We just need to look at this one. Because z minus 1 does not depend on x, I just take it out from the integral. And then look at this integral. This integral is similar to this one. The only difference is this z is replaced by z minus 1. Therefore, z minus 1 is replaced with z minus 2. Therefore, this integral is simply the gamma function of z minus 1. Now, we have just proved that the gamma of z is z minus 1 times the gamma function of z minus 1. Alright, so this part will be soon proved. When z is an integer, okay, so z can be non-integer, but when z is an integer, we have gamma z equals z minus 1 times gamma z minus 1, and this part is equal to z minus 2 times gamma z minus 2, gamma z minus 2 equals z minus 3 times gamma z minus 3, etc. In the end, we get z minus 1 factorial times gamma of 1. And what is gamma of 1? Actually, gamma of 1 is 0 factorial. And we can also look at this integral here. We plug in z equals 1 here. And then gamma of 1 is simply the integral of e to the power of negative x. From 0 to infinity, that's very simple. The result is 1. Therefore, gamma of 1 is 1. Again, gamma of 1 is 0 factorial. Gamma of 2 is 1 factorial. All right, and we just proved that gamma of z is z minus 1 factorial for integers. This is good. And then, because this integral is a continuous function, so look at this integral. It's a continuous function in the positive range, and it's smooth. So this function not only works for those integer data points, integer z's, it also works for those non-integer z's. All right, so now let's look at 0.5 factorial. When z equals 1.5, gamma of 1.5 is this. We just plug in z equals 1.5 here, all right? And then we just need to evaluate this integral, because this integral is simply gamma of 1.5, and that's 1.5 minus 1 factorial, it's 0.5 factorial. So really, 0.5 factorial is this integral. And we know how to integrate this kind of functions. Okay, we'll work on this. First, variable substitution. If you see x to the power 0.5, always convert it to, something simpler. So let's set x to be u squared. Then x to the power of 0.5 is simply u. And then we got u here. And then x is u squared. X is u squared. Okay, we're almost there. All right, and this, we can simplify it, because du squared is 2u du. Therefore, 2u times u, we get 2u squared. So it's this integral. It's just a Gaussian function times u squared. All right. So now we'll have to use a little bit trick here. Let's look at this first derivative of u times e to the power of negative u squared. So first, the derivative of u is 1. So it's going to be 1 times the Gaussian function, and then minus u times negative 2u times the Gaussian function. So u times negative 2u is negative 2u squared. So we have this here. And then both sides multiplied by du. We got this equation. All right? So the right-hand side becomes the left-hand side. The left-hand side becomes the right-hand side. And again, both sides were multiplied by du. And by looking at this, we realize that this 2u squared times the Gaussian function times du. So this part, this part times du is simply e to the power of negative u squared du minus this guy. All right, so from here to here, that's just very simple algebra. All right, and then we are looking at this integral, the integral of this part. Therefore, the integral of this part is the integral of the Gaussian function minus the integral of the exact differential of this product. So it's written here. All right, this part is simply 0. Why? The integral of the exact differential of a function is this function itself, right here. We plug in 0 and infinity. When u is 0, this function is 0. When u is infinity, this function is still 0. So this function disappears. So 0.5 factorial is simply the integral of this Gaussian function from 0 to infinity. And this Gaussian function is actually square root of pi over 2. So it's roughly 0.886. We will prove this integral is equal to square root of pi over 2 later. All right, so just for now, just believe me. 0.5 factorial is equal to this, the integral of e to the power of negative u squared, and this e to the power of negative u squared is square root of pi over 2. All right? So now we can compute 1.5 factorial, which is 1.5 times 0.5 factorial, which is 1.5 times square root of pi over 2. So it's 3/4 times the square root of pi, and we got a number here. And this number is greater than 1 but less than 2. Oh, by the way, this number is less than 1. So this number is smaller than 0 factorial and 1 factorial. All right? Okay, how about 0.25 factorial? Well, similarly, we can just evaluate this integral. It's complicated. We do some variable substitution. It's going to be this. This is still very complicated, but the result is this. Okay? Now, 0.55 factorial is 0.5 times 0.5 minus 1 factorial. Again, n factorial or x factorial equals x times the factorial of x minus 1. Therefore, 0.5 factorial is 0.5 times the factorial of 0.5 minus 1. So over here, you see this 0.5 factorial. And this 0.5 factorial is square root of pi over 2. So we have this result here. And then, therefore, the factorial of negative 1/2 is, well, over here, this guy is square root of pi over 2 times 2. It's square root of pi. It's 1.772 approximately. So now we just proved that the factorial of negative 0.5 is the square root of pi. The only thing we didn't do is we need to evaluate this Gaussian function. So over here, I'm going to show you how to do that. Let's look at this Gaussian function here. This is the integral of Gaussian function. It's the square root of this Gaussian function times itself. And then I'm doing variable substitution. This z is replaced with x. This z is replaced with y. So we got this over here. And then what we do is we just combine these two. These are two single variable integrals. So we can combine them. So we have a double integral over here. And this double integral can be rewritten in polar coordinates. So look at this. We are integrating this function over the entire two-dimensional space. We can do that using this different volume element for the two-dimensional space. It's r dr d theta in polar coordinates. R is from 0 to infinity. R is the radius. Theta is from 0 to 2 pi. Theta just is the angle. Again, if you have theta from 0 to 2 pi and r is from 0 to infinity, you cover the entire two-dimensional space. And what about this e to the power of negative r squared? Again, r squared is x squared plus y squared. And x is r times cosine theta. Y is r times sine theta. The volume element dx dy becomes r dr d theta. This is to ensure that this is the area of a volume element. Now it's simple to integrate this. First, we need to integrate this e to the power of negative r squared times r dr is here. And second, we need to integrate over this theta. It's easier. This part is just 2 pi. The integral of d theta from 0 to 2 pi is just 2 pi. So that's really easy. It's just I want to make sure that okay, so there's some kind of format problem. All right, now it's good. Now it's good. All right. So how do we do this? Remember, this RDR is 1/2 times the exact differential of r squared. I'll show you. So I'm going to multiply. Oh, this is 2 pi. 2 pi is here. I'm going to put a 1/2 in front so that this r becomes 2r. And 2r times dr is dr squared because the first derivative of r squared is 2r. Okay, the first derivative of r squared is 2r. So dr squared over dr is 2r. So that's why. And then we do variable substitution. We set t to be r squared, and then we get this simple e to the power of negative t times dt. This is a very simple exponential function. The integral of this is negative e to the power of negative t. And then we have the lower bound, we have upper bound. You do the plug them in, you get just 1 as the value of this integral. And therefore, the result is the square root of pi. And don't forget this. We were evaluating this integral from negative infinity to positive infinity. However, we want to know what's the integral from 0 to infinity. Fortunately, we know this Gaussian function is an even function. Therefore, the integral on the left-hand side is equal to the integral on the right-hand side. So on the right-hand side, the integral is just 1/2 of this square root of pi. So that's why we have the integral of this Gaussian function is equal to square root of pi over 2. This is very important. And also, this z is a dummy variable. I'm going to replace the z with u. Therefore, the integral of e to the power of negative u squared du is also the square root of pi over 2 if u is from 0 to infinity. So that's right here. This guy is simply square root of pi over 2. And then, again, now you hopefully have seen the whole derivation and believe this 0.5 factorial is simply the square root of pi over 2. And because of the definition of this gamma function, really nice gamma function here, that connects all the dots, all the integer dots, and we have this 0.5 factorial equals 0.5 times negative 0.5 factorial, and now we have this guy is equal to square root of pi. What about negative 1.5 factorial? Well, it's very easy because this guy, negative 0.5 factorial, is equal to negative 0.5 times negative 1.5 factorial. So you pretty much just use this divided by negative 0.5. Therefore, the factorial of negative 1.5 is negative 2 times square root of pi.